Hello everyone. Welcome each one of you to another session of peer teaching. This is a shared class done by myself, Aleena Elsa Raj.
I am Bodhi.S Dharman.
Myself, Surya S Karun.
Okay, so as you can see in the screen, today we are going to discuss about transition elements. So often the terms transition metal or element and D-block elements are sometimes used as if they mean the same thing, but they don't. There is a subtle difference between the two terms. First of all, we can look at what is this D-block elements. You will remember that when you are building the periodic table and working out where to put the electrons, something odd happens after argon. At argon, the 3s and 3p levels are full. But rather than filling up the 3d levels next, the 4s levels fills instead to give potassium and then calcium. So only after that do the 3d levels fill. So here is a pictorial representation of the shortened form of periodic table. The elements in the periodic table which corresponds to the D sublevels filling are called D block elements. Here you can see the first row of these is shown in the shortened form of the periodic table. Here you can see from the atomic number 21, that is the element scandium to zinc. Here it is represented the D block elements. And moving to the electronic structure of the D block elements, you can see here I am depicted the electronic structure of scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. While going through the electronic structure, you see there is an irregularity in chromium and copper. So let's see what is the reason behind that. This is something that you are just going to have to accept. There is no simple explanation for it which is usable at this level. Any simple explanation which is given is faulty. People sometimes say that a half-filled d level as in chromium, that is with one electron in each orbital, is stable, and so it is sometimes. But you then have to look at why it is stable. The obvious explanation is that chromium takes up the structure because separating the electrons minimizes the repulsion between them. Otherwise, it would take up some quite different structure. So now let's see what is this transition elements in detail.
So, as we have discussed about the D block elements, and we are now going to the transition elements. Okay, a transition element is defined as the one which has incompletely filled d orbitals and in its grounder state or in any one of its oxidation states. That is, a transition element should have an incomplete d orbitals in one of its ground states or on its oxidation states. So, a transition element should have an n-1 d orbitals, partially filled n-1 d orbitals. Transition elements are elements that contains an incomplete d subset, that is from d1 to d9 in at least one of the oxidation states of their compounds. That might be in the ground state or in the excited states. So here we can see scandium and zinc. Okay, in the case of scandium, there is 3d0. There is no elements, no atoms in the 3d series. And on this case of zinc, it is completely filled. That is, it is completely filled as 3d10. So next we are moving on to what is the difference between D block elements and transition elements. We have seen that the D block elements are different from that of transition elements. Okay. So all D block elements are no transition elements, but all the transition elements are belonging to the D block elements. All D block elements are no transition elements because D block elements like zinc have the full D10 configuration, as we have seen in the later slides, that the zinc have fully completed or completely filled D10 configurations in their ground state as well as in their common oxidation states, which is not according to the definition of a transition element. So all the D block elements are not transition elements, but all the transition elements belongs to the D block. Okay. So zinc and Scandium and zinc are not transition elements because they form compounds with only one oxidation state in which the D subshells are not incomplete. That is, in the case of scandium, it when converted to scandium 3 plus, it has 3D 0. And in the case of zinc to zinc 2 plus, it is having completely filled d orbitals as 3D 10. So as we have generally characterization of d block elements, or we have to be, this can be called as the d block elements versus the s block elements. The main characteristics of the transition elements are the physical properties vary slightly with atomic number across the series. In the series, the physical properties vary slightly with that of the atomic number. In the case of s block and p block elements, they have a characteristic features. Okay. Then the higher melting point and also higher boiling point, density, hardness than S block elements of the same periods. The D block elements have higher melting point, boiling point, density and hardness when compared to that of the S block elements of the same periods. And also the main characteristic property of transition elements how they have shown variable oxidation states as compared to that of the fixed oxidation state of S block metals. Okay. So now we are moving on to the variable oxidation states, and it was given by Bodhi.S.
Okay, now we are going to discuss about variable oxidation state or oxidation number. One of the key features of transition metal chemistry is the wide range of oxidation states or oxidation numbers that the metals can show. It would be wrong, though, to give the impression that only transition metals can have variable oxidation states. For example, elements like sulfur or nitrogen or chlorine have a very wide range of oxidation states in their compounds, and these obviously are in transition metals. However, this variability is less common in metal apart from the transition elements. Of the familiar metals from the main groups of the periodic table, only lead and tin show variable oxidation state to any extent. Examples of variable oxidation states in the transition metals. First example is iron. Iron has two common oxidation states. They are +2 and +3. In, for example, Fe2 plus and Fe3 plus. It also has a less common +6 oxidation state in ferrate 6 ion, FeO4 2 minus. Another example is manganese. Manganese has a wide range of oxidation states in its compounds, for example, +2, +3, +4, +6, +7. Next, we are going to discuss about the formation of complex ions. What is a complex ion? A complex ion has a metal ion at its center with a number of other molecules or ions surrounding it. These can be considered to be attached to the central ion by coordinate, that's dative covalent bonds. In some cases, the bonding is actually more complicated than that. The molecules or ions surrounding the central metal ion are called ligands. So ligands are molecule or ions surrounding the central metal ion. Simple ligands include water, ammonia, and chloride ions. What all these have got in common is active lone pairs of electrons in the outer energy level. These are used to form coordinate bonds with the metal ion. Some examples of complex ions formed by transition metals are Fe(H262 plus, CONH362 plus, etc. Other metals also form complex ions. It isn't something that only transition metals do. Transition metals do, however, form a very wide range of complex ions. So these are the stable oxidation state of transition elements.
Okay, so in this session, we have discussed about the transition metals, its factors, and what are the factors that affects the transition metals. So hope all of you get the concept. Thank you and have a nice day.